So, chapter 1, Sobolev spaces. Let me start by giving you some motivations for what we're going to be doing here. So, let's think that you're trying to solve a partial differential equation. Something like minus Laplacian u plus lambda u, say out of point x equal to f of x for all x in Rd, where lambda is some fixed positive number. So this is a linear equation taking the Laplacian here, so the sum of the second partial derivatives, or multiplying by a number are linear operation. So what we're trying to do here is we're trying to, given lambda and f, find u such that the partial differential equation holds, such that PDE holds. Now, this is a linear equation, so this is similar to solving an equation like this, like a times u plus lambda times u equal v in finite dimensions. So given v, a vector in Rd, find u in Rd such that this linear equation holds where A is a d by d matrix. Now, solving this linear equation in finite dimension in linear algebra is something you know how to do very well. So solving LE amounts to finding out whether or not A plus lambda identity is invertible, right? And you have very good techniques in linear algebra to decide that. You can take a determinant, for instance, and this is really the starting point of spectral theory. This is asking whether or not, maybe it's nice to put a minus in that case, whether or not lambda is an eigenvalue of A. And if you can invert, then you have a solution, and the solution u of your equation is going to be minus a plus lambda identity minus 1 apply to v. So we want to do the same thing for our partial equation. We would like to be able to say that minus Laplacian plus lambda identity is invertible. So lambda is not something like an eigenvalue of the Laplacian, and we would like to get the solution to our PDE by applying that inverse, finding out what that inverse may be, and applying it to the right hand side term f. Now, the difficulty in doing that is that, well, we're not doing linear algebra in infinite dimension. In finite dimension, over the reals, there's only, up to isomorphism, one vector space of dimension d, which is Rd. So we knew very well that, if I have a data v in Rd, I need to find a solution in Rd. But in infinite dimension, this is a little bit more complicated because we have a whole variety of possible infinite dimensional vector spaces we can use. So I've been very imprecise when I said given f, lambda I told you was a positive number, but I didn't tell you in which space f and u are supposed to live, and that's very much part of the problem. So we want to be able to say given f in some space there exists a u and some other, and ideally a unique solution and some other space. So the choice of space is very much determinant in the problem. Now, it would be tempting to say we could take u, say a twice continuously differentiable function on Rd. That would be natural, because that would allow us to make sense of Laplacian u, and Laplacian u will be a well-defined continuous function on Rd, and that's very much the classical way of doing partial differential equation, we'll see that from a functional analysis point of view, this is really not a very good idea, because the space of continuous function is a very nasty Banach space. There's very limited analysis we can do in such a space. On the other hand, in analysis 2, you've seen that very good spaces from the point of view of analysis are Hilbert spaces. So the answer is going to be that we're going to take F in L2 of Rd, and then we're going to be looking for a solution in a certain subspace of Rd, which I'm going to call H1 of Rd, the Sobolev space H1. So the space in which we will decide to work is a subspace of the Hilbert space L2 of Rd. And we would have very good theory. You already know enough functional analysis in Hilbert spaces to answer this problem, to start understanding what the eigenvalues say, or analogs of eigenvalues of a linear map such as the Laplacian may be when working in a Hilbert space. So this first chapter is about understanding what this space should be, what appropriate subspace of the Hilbert space L2 one should use when dealing with differential operators. So let us define the Sobolev space H1. We start with an open set of Rd. We can take the full space, but we can also take a proper subset. And then H1 of omega will be the set of functions that are in L2 of omega, but also happen to have a first derivative in an L2 sense. So that's what we call a weak derivative. Now, what do I mean by a derivative in an L2 sense? Partial derivatives, there's d of them if I'm in d dimension in an L2 sense. I mean some element of L2 that acts like a derivative when integrated against a test function. So you look at any function that are C infinity and compactly supported inside omega, and you use integration by part not as a property of functions that are differentiable, but as a definition for the derivative. So you say that if you look at this quantity on the left-hand side, where you're taking the partial derivatives of phi, which you can certainly do because phi is C infinity. Now, if you had a partial derivative of f, you could do integration by part and get this right-hand side with gi equal d partial derivative of f. But now we're going to say that f has a weak partial derivative if there exists a gi, which may not be a continuous function or anything like that. It's just an element of L2, but it satisfies this property, which is a version of integration by part. And then this gi will write di of f instead of gi, so we'll use the notation for partial differentiation, but we'll keep in mind that this may not be a partial derivative in the classical sense, like as a limit of increments of f divided by the size of the increment, but we'll call that a weak partial derivative. It is defined through the integration by part formula. So this defines a certain subspace of L2, and I'm going to put an inner product on that subspace. And the inner product I'm going to define, so this is my notation for inner product in all of my Hilbert spaces. It's going to be, part of it is going to be the inner product that we use on L2, which is just the integral of the product of the function, but I'm also going to add to it the integral of the product of the gradient of the function, the first derivatives of the function u and the function v. So this gives an inner product. Well, you have to show that. This is exercise 1.2. I'm going to leave that to you to show that this defines a Hilbert space. So you need to show that this defines a inner product. And then when I take the inner product of u with u and raise that to the power 1/2, then I get a norm. And well, it's pretty clear to say that this norm is going to be in general larger than the L2 norm, and that's going to make H1 a subspace of L2 continuously embedded into L2. So I'll leave that as a good exercise for you to show that this define a Hilbert space, a subspace of L2 of omega, which is itself a Hilbert space. And that's really the subspace of all those functions for which you can make sense of a partial derivative in an L2 sense. So we've just introduced weak derivatives, and now we want to see that this notion is a proper generalization of the classical notion of differentiation. More precisely, we're going to prove that the space of one continuously differentiable function on an interval, say minus 1, 1, is included but not equal to the Sobolev space over that interval. And that's telling me that if I have a standard derivative, then it is a weak derivative. But not all weak derivatives are standard derivatives. I'll give you an example of something that is in H1 but not in C1. And that's because you have much more flexibility when you're looking for a weak derivative as an element of L2. So L2 being a space of equivalence classes of functions up to almost everywhere equality, as opposed to being, say, continuous function, which is a much more restrictive notion. So we're looking for a derivative in a wider space. Right, so let's see how that works. So let's go first for the inclusion. Let's give ourselves an f, that is C1 minus 1, 1, and let's give ourselves a test function phi that is C infinity and compactly supported on minus 1, 1. Now the first thing I want to remark, now I'm looking for this weak derivative, and I'm expecting that the standard derivative might be the weak derivative. But a weak derivative, gi, in my definition, has to be an element of L2. So the first thing you need to make sure of is that f prime, if it's going to be your weak derivative, is in L2. Now that is the case because if I do the integral of f prime x squared dx between minus 1 and 1, is that finite? Well, yes, because this is smaller than 2 times the supremum of f prime over the interval, the compact set minus 1, 1, and f prime is a continuous function on a compact set, therefore it's finite. Therefore it's bounded. So my f prime is square integrable. Of course it's measurable because it's even continuous. So we have that f prime is indeed in L2 of minus 1, 1. Does it satisfy this integration by part formula? Yes. Why? Well, by integration by parts. So let's check that. If I integrate between minus 1 and 1, f of x times phi prime of x, and I apply integration by parts, I get f of 1 phi of 1 minus f of minus 1 phi of minus 1 minus the integral from minus 1 to 1 of f prime of x phi of x dx, and phi of 1 and phi of minus 1 are going to have to be 0. And that's because phi is compactly supported on minus 1, 1. And the upper interval minus 1, 1. Okay. So this has to be equal to minus the integral from minus 1 to 1 of f prime of x phi of x dx, which is the defining property of my weak derivative, and that is telling me that f belongs to H1. So I have an inclusion. Is that inclusion a proper inclusion? Or do I have equality? It is proper, and here is the example to show that the inclusion is proper. So I'm going to define f of x to be equal to the absolute value of x for all x in minus 1, 1. Now you know that this is not differentiable at 0, but I'm going to define something that is going to be a weak derivative. So I'm going to define g of x to be equal to minus 1 whenever x is between minus 1 and 0. I'm going to define it to be equal to 1 when x is between 0 and 1, excluding 0. As you would expect from a derivative of f, which is equal to minus x for negative x and just x for positive x. And then at 0, Well, I can really define it to be whatever I want because I'm only going to be looking at it in L2, so it's only defined almost everywhere. So whatever value I assign to G 0, it's not going to change G as an element of L2. So let's put that equal to 2020, why not? If x is equal to 0. Okay, so I've defined that G, and I'm claiming that G is the weak derivative of f. So let's see if that's true. Now G is certainly in L2 because it's piecewise constant. And does it satisfy the integration by part property? Now let's take a phi that is C infinity and compactly supported in -1, 1, and let's compute what is the integral from -1 to 1 of f of x phi prime of x dx. You can cut that into two parts, the part between -1 and 0 where f of x is equal to -x, and the part from 0 to 1 where f of x is equal to x. And then you can use integration by parts on both parts, and for the first one you're going to get minus phi of -1, which is 0, and minus the integral from -1 to 0 of the derivative of -x, which is -1 times phi of x dx, plus the integral from 0 to 1, plus phi of 1, which again is 0 because phi is compactly supported, minus the integral from 0 to 1, derivative of x is 1 of phi of x dx. So all in all, this is equal to the integral from -1 to 0 of phi of x dx minus the integral from 0 to 1 of phi of x dx. Now on the other hand, if you look at minus integral of -1 to 1 of g of x times phi of x, then what do you get? Well, you can split it again into the interval from -1 to 0, where g happens to be equal to -1, plus the integral from 0 to 1, where g happens to be equal to 1, and you get exactly the same thing. So the integral from -1 to 1 f of x phi prime of x dx is equal to minus the integral from -1 to 1 g of x times phi of x dx. So g is the partial derivative, well, there's no partial here, it's one dimension, it's the derivative of f in the weak sense. Okay, and really what makes this possible, as you can see here, is that because we're integrating everything, the value of a function at a point doesn't matter. And we're only looking at equivalence classes up to almost everywhere equivalence, because integrals don't see values at one single point. So the fact that f of x in a classical sense was non-differentiable at exactly one point really didn't matter from the point of view of weak differentiation. So the next result in the note is called Corollary 1.4, and it gives an answer to the question that I was mentioning when I gave you motivation for this notion of weak derivatives and Sobolev space. Now, what is Corollary 1.4 telling us? It's telling us that if you look at the problem, minus Laplacian u plus lambda u equal f, you have a solution to that problem in L2 in the following sense. So you can invert the operator, you can find an inverse to the operator minus Laplacian plus lambda e acting on L2 of omega. In particular, lambda is definitely not an eigenvalue of the Laplacian. And more precisely, our statement is that you can give yourself any positive lambda, any f in L2, and you can find a unique element of L2, which actually is going to be a unique element of H1, and using the subspace H1 is critical here, in particular from the point of view of uniqueness, such that if you test against any element in C infinity compactly supported function, you have this equality, but in the following weak sense. So what is that telling us? It's telling us that you're integrating the equality multiplied by v, but you're not writing minus Laplacian u times v, you're performing, if you want, an integration by part and writing grad u grad v instead, so an element of the inner product of h1. So we know that this makes sense for any u in h1 and any v in C infinity compactly supported. So this is a weaker notion of solution. We're not looking at the equation at every point x in omega. We are looking at an integrated version tested against any C infinity function. So it's an equality of derivatives of the functions and the functions themselves, but it's an equality in the weak sense, so purely in the sense of weak derivatives. So this concept of looking at things weakly will be a theme throughout the course. We'll see as the course progresses that there's really an idea of weakening topologies that's hidden behind this formulation, and by weakening the topologies we are getting existence result for more problems. So we've weakened our notion of solution to a PD in order to make the existence question easier and a lot more natural from a linear algebraic point of view. That being said, in doing that, we're not completely cheating. As we will see a tiny bit later, there's a regularity theory that tells you that actually this solution, this weak solution to the problem, is in fact a classical solution. So in fact, you will have to be twice differentiable, and this equality will hold not just in this somewhat weird, at first glance, integrated sense, but in a everywhere sense. But the advantage for now of this formulation conceptually is that it makes the problem very much a linear algebra question. And indeed, this result is going to be a direct corollary of a more abstract result about bilinear form in Hilbert spaces. And that theorem 1.5, due to Lax and Milgram in 1954, it's a generalization, if you want, of the risk representation theorem. And it tells you that if you have a bilinear form on H cross H with value in R, that is continuous, this is this notion, it's really a bilinear version of the continuity of a linear map, and it happens to be coercive, and that is to say that the quadratic form associated with your bilinear map, A of UU for one fixed U in H, is not too different from an inner product, and it's comparable to the norm on your Hilbert space up to some constant delta here. Right, so if we have such a bilinear form, and in this problem, taking uv goes to integral of grad u grad v plus lambda integral of uv will be a perfect example of a continuous and coercive bilinear form. I'll let you check that as an exercise. Then we're going to find that any equation of this form, a of uv equal phi of v, for phi a continuous linear function from h down to the real, as a unique solution. So there's a whole range of abstract PDE type problem, this is what I've highlighted here, that have unique solutions whenever they are defined in terms of a continuous coercive bilinear form. And then there's a subsequent part to the theorem, which is a variational characterization of this solution. So this sort of equation, A of uv equal phi of a, will always have a unique solution, thanks to the Lax-Milgram theorem. But if A is even nicer, it's a symmetric bilinear form. A of uv is A of vu for all u and v, like what you have when you deal with a inner product. Then you're going to have u as the unique solution to a minimization problem, minimizing this quadratic form here, 1/2 of avv minus phi v. And u would be the unique element in your Hilbert space that minimizes this functional. So that relates an abstract PDE problem, which is what we have here, to an abstract minimization problem, just like you have in in physical situation where you have a partial differential equation describing the minimizer of a certain energy functional, typically speaking. So as we progress in the next couple of lectures, we're going to prove the theorem by Lax and Milgram. And as you can guess from this variational formulation at the end, this is very much tied up with understanding optimization question in potentially infinite dimensional Hilbert spaces, which is what we're about to look at next.